Hello viewers, welcome back to the lab. Today's video is going to be a teardown, which is great because it's about time we did one. So it's been a bit difficult picking up interesting items of late, but this came up on my radar and very much caught my eye. Unfortunately, originally this was priced way beyond anything I could afford for a teardown, so I had to sit and watch the auction end with no bids so I could make an offer to the seller. Now thankfully all this worked out and it's now here for you all to see inside. Now it's down to my patrons that allow me to purchase items like this, so thanks go out to them for their support. If you want to join them by throwing some coins into the hat, then links will be in the video description and up there in the corner. So we have here a Rigaku Saturn 724. It's a special kind of, I would like to call it a camera, but it might be more appropriate to call it an imaging device. As you can see here, there doesn't appear to be any kind of lens or optics on the front, so what's the deal? This is an imaging device used in X-Ray crystallography. It's effectively an X-ray camera. Now, X-ray crystallography is a technique where you generate a collimated beam of X-rays, send them through a crystal, and as the internal structure diffracts the beam, it generates a pattern, and by imaging that pattern using a motorized rig and software, you can generate views of the internal structure of the crystal in 3D. So if you look here, what I'm doing with this laser, I'm just shining it through a piece of glass, and as I just move the glass around, you can see that the image slightly changes, and this is effectively the same principle that's involved in crystallography. You shine the X-rays through the crystal and it generates a pattern, and you can move the item around and take individual pictures, and then with some software you can regenerate the internal structure. As I said, it's not quite comparing apples to oranges here, but it's the principle is similar. Right, let's take a quick tour around this. We've got a big metal box. It weighs about 8-9 kilos, so yeah, it's fairly substantial in weight. We have the cooler arrangement on the top. This is plumbing for a cryo cooler. We've got a power input socket, a reset button, nothing on the sides. On the back we've got some vent holes, a small screen for displaying status, things like that, and up on the top here we have 2 fibre optic ports, one for trigger and one for data. And on the base here we've got a large mounting plate which has been attached to the bottom, so this would have been installed on the big rig. Obviously it would have all need to be mounted very, very securely. Now this looks a little bit like amulite. I'm not sure whether it's prefabulated or unfabulated, but I guess it could also be aluminium. After doing some research, it seems this camera is totally dedicated to doing crystallography. The camera and its software are specialised to the task. It seems to be introduced by Rigaku in about 2007. Rigaku are a Japanese company with offices around the world. It seems they specialise in this kind of X-ray crystallography and X-ray diffraction. So very, very specialised bit of kit. Unfortunately, I've not been able to determine the cost of this camera, which is a bit of a shame. It's not going to be cheap. It's going to be many tens of thousands of pounds. Right, so what is actually going to be happening in this camera? So as I said, this will be mounted on a rig. You'd have the sample and then a collimated beam of X-rays which would go through the sample and then strike this screen. Now this screen on the front here is just a protective piece of plastic. It's probably going to be completely opaque to visible light. Behind that there is going to be a phosphor screen which, when it's actually struck by the X-ray beam, and then re-emit those as visible light. Then behind that there is going to be a large fibre optic taper which is going to take the imaging area on this front here, which is about so big, and then that's going to shrink down onto the actual size of the CCD. So the reason why they do that is it gives you a bigger working area to project the diffraction pattern onto. Now the CCD itself is going to be cooled to reduce the noise, and it's going to be mounted inside a vacuum chamber, which aids in the cooling and also prevents any condensation issues. Now I should say I have actually already been inside this. What I wanted to do is release the vacuum in the chamber before I started filming, because I just wanted to do it in a controlled environment. I didn't want to be doing it halfway through filming the teardown. So I have been inside and I've released the vacuum, so it's all at atmospheric pressure now. Right, before we take the top off, let's have a quick look at the cooling mechanism. This is actually a cryo cooler, so this is basically a refrigeration system. To go with this camera there would have been a compressor which would be compressing the refrigerant and pumping it through this, which would then cool down the CCD. Now you can see here we have two tags on here, one green, one red, NF55. Quick bit of research shows that it's quite a common refrigerant. It cools down to about -56, it seems. There's two, so there'll be an in and a return. I presume the red one is the outlet and the green is the inlet. Now this is actually has an ID tag on it, and it's manufactured by Brooks in Automation, and it's part of the Polycold cryo coolers. I think they used to be called Cryo Tiger, which is why they have the Cryo Tiger name on there, and it's the cold end obviously because it's the bit that gets cold. So the lid was just held on with 4 Allen screws up on the top here, so this just slides off. So what I'll do, I'll just move this round, spin it round, and actually point out all the major components of it. So at the front here we have the phosphor screen and the fibre optic taper mounted on this large aluminium plate. So if I turn it around a bit further, we have a large circuit board here with some either shielding or possibly heat sinking arrangement there. There seems to be a little daughter card which is plugged on this one. This is actually described as analog mother, so presumably this is the analog section which takes the data from the actual CCD itself. We've got a couple of connections. We have what might be a heater in the front here. This little section here, this connector here is called heater con, so I think that's a small heater there, possibly to prevent condensation. We'll have a closer look at these boards in a moment. So if I turn it a bit further around, we can see the back. This looks more like digital processing. If I tip this forward, we can see 2 ports down on here, presumably for evacuating the chamber. We've got a nice big barcode along the bottom there, and that is the details of the actual CCD which is used in this. So if I turn it around a bit further, we can now see the connections from the power port and the reset switch, and we also have a Pirani vacuum gauge here, so this just measures the actual chamber pressure. And we can see a large metal chamber here, which is where the fibre optic taper is going to be, and then the CCD. And then on top of that we have a large tube which will hold the cryo cooler. Right, with those circuit boards off the camera now, I thought we'd just take a quick look at them. This is also an excellent opportunity to mention my channel sponsor, PCBWay, who continue to support this channel. They have a huge Christmas shopping event on at the moment, so if you're into having some prototype PCBs made, go check out PCBWay. Links will be in the video description. There's a huge amount of offers on at the moment, 70% off, cash coupons, all in time for Christmas, so go check them out. Right, so this board here is the board that's described as power, and indeed, yeah, there's a whole ton of power management stuff going on here, plus all the digital electronics. Right at the top here we have the two fibre optic connections, one for the data and one for the trigger. We also have a connector here for the pressure sensor, which monitors the vacuum inside the chamber. Just below that there is a Maxim RS232 driver, so they're obviously talking to that pressure sensor by RS232. Next along we actually have a USB port, and right above that we also have an FTDI RS232 bridge to USB bridge, presumably for diagnostics. Now I actually have a sneaky suspicion these caps are getting on the weak side. They do look a little bit domed to me, so it could be that this has been powered on for a rather long time and they are slightly domed, unless that's the just how they come out of manufacturing, but they are a decent brand. They're Nippon Chemicon. You can see more voltage regulation going on here, and just here we have another voltage regulator. We've got a JTAG connector, a couple of switches. One is labelled just SW1, so no idea what that one does. There's one here, vac pressure switch, so yeah, not really sure what that would be doing. Obviously something to do with the vacuum pressure, but why you'd need a button, I don't know. We've got LCD adjust, so that might be LCD contrast adjustment or something. We've got a coax connector there for shutter con, so not entirely sure what that would be used for and why it's hidden away inside. We've got an FPGA here, it's a Xilinx Vertex 4. Next to that we've got a large DC converter there with some of the magnetics actually enclosed in the circuit board there. You can actually just see the traces there. So more voltage regulation. I think you've got some RAM over here, presumably connected to the FPGA. And we have the LCD status screen, so I've just moved that out of the way. There's a few passives underneath. We've got a little bit more voltage regulation going on here. Let's move this a bit better into view. So some more voltage regulation, and we have another device down here, and that is a configuration PROM for the FPGA. Interesting, there's some little really nicely done little budge wires down in here. I'll just try and get you a better view on that. It's very, very neatly done. Let's just get you in. So yeah, you can see here there's a little budge wire. This is going to the LCD connector, so I think somebody had a little oopsie there. They've actually gone to the effort of actually standing those capacitors up on end and soldering a little budge wire on. As far as budge wires go, there are a few about. There's one on this USB connector. Looks like they might have accidentally swapped the two of the pins and they've had to put a budge wire in there to fix that. And on the back side of this this power board, we've got more voltage regulators, some more big bulk capacitors there, really enormous SMD caps. I've never seen any quite that big before. They're rated at 63 volts. So, and we have under here some this heat transfer stuff is it's like oily icing sugar. So we've got presumably 4 of these Betadine LN10D12/48, and they're DC converters. 48 volts in, 12 volts out. They are dual rail as well, so you've got plus minus 12 volts. So looking at this connector here, this is the main power input. We've got 1, 2, 3, 4, 5, 6, 7 connections. This pair is 48 volts DC. This pair are the ground, and then these 3 are operated by these 2 solid state relays. It seems to be that one is controlled by the power supply and one is controlled by this board, so I'm not quite sure how they interoperate together. A quick look up on the fiber optic port transceiver, and these are 2.5 gigabits per second. Right, let's have a look at the other board, which was analog mother. This is the back side. We've got the connector that went through to the pass-through connector into the vacuum chamber. Lots of tantalum caps and voltage regulation going on there. Not much on that side. Flip this over. And this is clearly the analog control side for the CCD. As mentioned before, the CCD operates in 4 quadrants, so everything's multiplied by 4. So we've got 4 little daughter boards here, which are the actual analog to digital converters. So these just plug in to little connectors there. There's a few there's passives on the back, and all the active stuff is on the top. This little thing here is just screening. It's just a piece of plastic that's been metallized. It's all multiplied by 4, 1, 2, 3, 4. So there's going to be a lot of clocking of all the data and sending out presumably through these two onto that other board where the FPGA will do all its bit twiddling to reassemble all the image data and actually produce an image that can be downloaded onto the computer. We've got another connector up the top here, presumably that's for all the control stuff. There's a couple of connectors on here. These were unused, these two. That is 2 pressure sensor, so it's odd that that's duplicated. So maybe these boards are used in other products. We've got that heater connector there, presumably switched, and turns on that heater, which we will have a look at in a minute. So if we have a quick look at one of these ADC boards, we have on here an Analog Devices AD7641, and these are an 18-bit 2 megasamples per second ADC. So yeah, quite tasty spec on that, really. And indeed, they are still a current product, and they are a snip at £40 each. So yeah, not a cheap IC at all. It's mostly just, well, it is just passives on the other side. Yeah, there's something big spring-loaded in there. There we go. Right, we've got a large spring plunger just in there. We also have one of the seals. Okay, so this looks all pretty simple in here. We've got the large chamber. We have the cryo cooler at the top with a large copper cold finger which comes down. That spring that was on the back plate pushes against this and makes a good thermal connection between what looks to be like an aluminium plate underneath, which then runs down onto the back of, presumably that's the CCD down in there. And we've got a few devices mounted on the back of it. We've got the board down at the bottom, and we have another board at the side here. Looks like it's connected with a large flat flex, and then comes through to that pass-through connector. Right, now we have the back removed from the chamber. We're just going to do the front so we can have a look at that phosphor screen and the fibre optic taper. Right, so there's just a couple of Phillips screws on here, so they should be fairly easy to remove off here. There's no other screws around the outside, so there must be something underneath here. more hex screws to undo, so let's see what size these are. So this front plate is just a big machined bit of aluminium with a plastic cover and a little bit of foam in there. Looks like we have what looks to be a bit of something, and presumably if I tilt this up a little bit. Yeah, so it's all a bit inconclusive. I'm not sure which bit is what. I'm certain this is just a fibre optic taper, and presumably this white disc in here is the phosphor. Oh, I think the O-ring's popped out. I can just see an O-ring. I can't push this back in. I think what is the CCD is actually attached to the back of this. So when I'm moving this, it's actually moving this in here. So what I need to do is temporarily reattach all this and then probably remove this. Actually, let's just take off this Pirani gauge. So this is where I actually released the vacuum out of the system. I just loosened off this fitting here. So that's the Pirani gauge. It's a 925 micro Pirani made by MKS. So it's a completely self-contained thing. Right, so let's take a look at the cryocooler. So the cryocooler is actually mounted inside this stainless steel tube. We have the cold finger at the end here. Let's just turn that around. So we have the output of the cryocooler tucked in there. Connected to that is a copper block, and it looks like we've got a sandwich of copper strips which come down and then mount to an aluminium block, which then attach to the back of the CCD. So the way this works is you've used a sandwich of, so the strips of copper just allow this a bit of flexibility and to allow it to move in and out and make contact with the back of the CCD. Now, interestingly, on the back of the aluminium block which mounted onto the CCD, we do actually have a couple of resistors. These are 10 ohm resistors. There's two of those. So a bit puzzled by that. I think what might be going on is there doesn't seem to be any control loop with the actual cryocooler, so I suspect that is probably just going to turn on and just chill right down to minus 56, and then they're pumping power into the block with these resistors to warm it up to the temperature that they want, because I think the minus 56 is probably a little bit much really for what they need. Looking at the datasheet for the CCD, there doesn't seem to be much benefit below about minus 10, so they're probably bringing the temperature of this back up to a certain point, and then they can just sort of control the temperature using these two resistors. So the cryo pump is just completely enclosed in Mylar film. Feels quite thick actually, that. Just for insulation. I'm not going to take that off because this should be worth a couple of quid on eBay, I would have thought, as a spare for somebody. So yeah, really cool looking bit of kit. Definitely looks like it's come out of the space program or something, doesn't it? One thought I did have was to take off this section here, which has what seems to be the heater in it. Oh no, there it is. So that's just that was easy, wasn't it? So yeah, they're just a couple of heaters. 120 volt, 250 watt. Now they wouldn't have been running at 120 volts because we've only got 48 volts running into this. So I guess they would have been running under. Now the problem is, even if I took this off and then took this whole section off, the PCB wouldn't fit through the opening anyway. So this PCB definitely has to come off. Wow, well that was a bit of a mission. That's off there. So we've got a flex rigid board, so we've got PCB. There's no solder mask or anything on that. And we have two flex sandwiched in it. So there's not much on this, some capacitors. And there looks like there might be 1, 2, 3, 4, 5, 6 active components on it. So they might be like preamps, just to get the analog signal from the CCD out to the board where it can be digitized. So we've got the two connections for those two resistors, and we've got a temperature sensor. So you can see in there the backside of the CCD. It seems extremely well attached to that fibre optic taper. Can't see any way that's mounted, but it does mean now if I remove this part, it should come out. Okay, I've realised that I can't take off the front without getting it under there because there's screws under there. That means that this has to come off that plate, and then that plate has to come off that plate. So a bit of a disassembly to do from here. So I need to take off that this plate here. Right, wow, doesn't that look expensive? So it appears as though the fibre optic taper is actually part of the CCD. Right, now looking at this CCD, I think what they've actually done here is they have purchased the CCD from Kodak without any glass on the front of the front of the chip, and what they've got is a fibre optic taper. Then they mount these ceramic sides onto the taper, and then glue the CCD onto those two pieces of ceramic. So the taper sits right down at the front of the CCD, probably with no glass or anything on the front of it. Don't forget, this is all installed in a vacuum anyway. So yeah, I don't think there's really any practical way to get that off without smashing it to bits. A bit of a shame really, because I would have liked to have looked through that fibre optic taper. That would have been quite a cool thing to look through, because effectively that's going to magnify. But yeah, it seems to be permanently attached, so no chance of getting that off, I don't think, unless anybody's got any bright ideas. Right, so if we have a look at some of the bullet point specs of this CCD, The KAF 4320 image sensor is a high-performance monochrome area CCD charge coupled device image sensor designed for a wide range of image sensing applications. The sensor incorporates true two-phase CCD technology, simplifying blah 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 blah. Sensor also utilizes TrueSense transparent gate electrode to improve sensitivity. Blah blah blah. So we have total number of pixels 2092 by 2093. Active are 2084 by 2085. 4.3 megapixel. The pixel size is a 24 micron and it's square, so 24 by 24. Active image size is 50.02 millimeters. That's square, which is enormous. 50 millimeter active image area. The die is 52.3 by 52.7. Wow, that is an enormous bit of silicon. Yeah, I wonder how many wafers you had to go through before you got a good one. 4 outputs, as we noted before. Dynamic range is 20,000 to 1. Maximum data rate is 3 megahertz. Part number, so we have here the KAF 4320 AAA, and the marking on the back is AAA JPB2. So that was originally monochrome, no micro lens, PGA package, taped clear cover glass, no coatings. I've never actually found a price for the actual single unit. They were available on DigiKey, it seems, but they're now discontinued, so the pricing's disappeared, so I can't actually see how much they would have been. So yes, a very specialised and expensive CCD there. So I hope you enjoyed this one. Don't forget, more teardowns are always on the way. Share, like, subscribe, comments are always welcome. Thank you very much, and I'll see you on the next video. Bye for now.